So hi everyone, and now we are going to talk about computational proteomics for the post-translational modification. So I know that the last days we heard several times about PTM. So almost all of our plenary speakers talk about some PTMs, like we started maybe the cancer for the phosphorylation, and then we heard about the protein histidine phosphorylation. And even today, Dr. Paolo Picotti was mentioning about osmotic stress, and then on the pathway there was some phosphorylation event occurring. And so I know some of you already studied the PTMs, but let's put all of us in the same level. And here comes our Superman. So Superman is just a random guy, right? During day, he's just a Clark Kent and no one really cares about him. But when there's innocent people in danger, he turns a Superman, he gets his superpower. Like our protein, when some stresses, some other event happens, then they get their PTMs and they have their superpower with these PTMs. And now I will talk about in the beginning what are these phosphorylation, the PTMs, and then I will talk about the spectra for modified peptides and what do we need to know to identify these modified peptides, and how we can set the MaxQuant, and what about the computational aspects in the MaxQuant for PTM studies, and the conclusion. Okay, so let's make a simple example for post-translational modification. As I say that they are playing a crucial role on our biological process, and then many times we heard about the kinase. So let's briefly show on the schematic version how this kinase works. So we have a protein, and then we have this enzyme called kinase. And what the kinase does, kinase simply adds phosphate group from ATP to our proteins. And as a result, our proteins are phosphorylated and they play some other biological processes. And it's also possible this reaction is reversible. And then this phosphate group from protein loses this phosphate group by using the phosphatase. And then the phosphatase gives a phosphate group to the ATP. And in the end, we know that this phosphorylation event happens on the serine, threonine, tyrosine. And what's known that this is so important in our biological sample, as a result, we got the discoverer guys who found them, they've got the Nobel Prize. This is very important, and we could also see it involves several different processes. And PTMs, people spend their time, several years on these studies. And here on the right, we could see that the process is regulated by phosphatase. This comes from this review paper. And then what we see, these are the top selected processes from the phosphate sites, some like the website that I will show later. So as you see here, there's a transcription, and the transcription is actually very actively, there are many phosphorylation events happening over there. And the second one is the cell growth and the cell cycle. So when the phosphorylation event happens, when the PTMs happens in this case, so the proteins are changing their role, and then they transfer the signals. But what's important that to understanding these PTM events, like we heard also several times this kinase is related to the cancer, because when there's some irregularities, there's this order happens on the phosphorylation, it leads to diseases. So that's why many companies actually focusing on studying this kind of events, and the kinase is quite popular in the drug development, but it's not the only PTMs that's being used. So we also see a lot of ubiquitination also in the drug development companies too. So we have because many people are actually working, so there's a very global center called Phosphocyte Plus. This is the website. And then maybe the name is a bit misleading, but here we could have information about the phosphocyte studies. So what about the sites and where they are playing the role? And it's not just only about phosphorylation, we could also see here the ubiquitination, and also as you see on the third one, the first one is the acetylation as well. So let's agree that the phosphorylation, PTMs are very important to understand the biology, but we all came here to understand how mass spectrometry can help to address such question. So to understand this, now we check how the spectra looks for the modified peptides. So on the mass spectrometer, what we measure the mass to charge ratio of the analytes. And here in this scenario, we have two peptides, peptide A and peptide B. On the peptide A, it's a unmodified peptide, and the peptide B is actually a modified peptide. As you see, there is on the fourth residue, we have a star, and star just representing some PTMs over there. And we know our mass spectrometer is very sensitive, so we could see this mass changes on the spectrum. So what we do in the beginning on the mass spectrometer analysis, we do the MS. On this MS, we have the peptide masses. And then here, the differences between peptide mass A and B is corresponding to the modification of the mass. But so here in the MS1 level, we have the information about the complete peptide mass, but we don't know the identification. What is this, the peptide sequences? To understand, to find out the peptide sequences, we do the MSMS. On this MSMS spectrum, we see that we have the fragment ions, and then the smallest one has E, and the next to this peak is we have DE. And so all of them has the fragments containing from this part of the residue. But for the peptide B, what we see here, there is a star for the modification. So there is this shift also on MS2 spectrum. So the shift only happens when our fragment ion contains this PTMs. And most of, like, sometimes we don't know the PTMs, and then we go to dependent peptides, but when you are focusing on the phosphorylation or the others, we know where the PTM is happening, which residue is happening, and then what about the mass shifts. So it's also important to understand the peptide fragmentation, because different fragmentation methods result in the different fragment ion types. So here what we see the peptides, the schematic version of the peptide, and we have N-terminus and C-terminus. And the fragmentation happens on the peptide backbone. And usually on the green one, so this is the peptide bond, and then here and then we have B and Y ion. And B ions are the fragment ion containing the N-terminus, and the Y ions are containing the C-terminus. But of course, it might be happen this one before, then we have A and X ions. It could also happen one after, then we have C and Z ions. So in theory, we have three different main fragment ions. But on the fragmentation method, it's important for us to, on the database search level, but it's also important to understand if there's another diagnostic peaks or neutral losses. So neutral losses is like losing the water or ammonium, and they are the loss. So we don't, and only in this fragments, on the fragments ions, we are just losing this water on ammonium losses. But the diagnostic peaks are different. So here we have ammonium ion. About the ammonium ion is the internal fragments. So it is between X and Y. We have this pieces, and then this has very special characteristic for the phosphorylation. When it was phosphotyrosine, this ammonium ion came together, and it's very special for the phosphotyrosine. So this diagnostic peaks, we see it, and then this we also use it for our database searches engine later on. So there are commonly used fragmentation methods. We have collision-induced dissociation, we have higher energy collision-induced dissociation, and then we also have electron transfer dissociation. And they all give different fragment, I mean, not all, but like two different fragment ions. Now let's go to what we need to know to study modified peptides. So CID is used for studying peptides, but it's not ideal for the modified peptides. So here we see the peptides, and it has a phosphorylation on the third and the fifth residue of serine. And what we see here, we see mainly B and Y ions because it's CID and we cut it on the peptide bond. And then our spectrals are noisier and we have a lot of smaller peaks over there. And the other thing is CID, we are losing the labile bond of the PTMs. So therefore, we tend to not to study CID for phosphorylation. And then we also don't have low M over Z fragments ions. So this phosphotyrosine, this diagnostic peaks, is a low M over Z range, and it will be below 200 M over Z. And then in this case, as you see, the spectrum starts about 200 M over Z. So we will miss this kind of special diagnostic peaks too. But on the other hand, for CID, we can study PTMs in a better way. And if you look at this, the same peptides on different fragmentation on CID, we see that we can observe the lower M over Z. So if you look at the x-axis, we could see that it goes below 200 M over Z. And then we could also see that we have more Y ion than the B ions. And the spectrals are much more cleaner. So we don't have this smaller noisy things background on our SCDs. And then there's another special thing about SCD. This B2 ions became to A2, and we don't detect actually on the CID. So we can use the CIDs to study PTMs, but that's not the only technique. So there's also another fragmentation method. This is electron transfer dissociation. So what we need to know that the method works different than SCD. And then here we are transferring the electron. And as a result, we don't cut it on the peptide bond, but amine bond. Because we don't cut it on the peptide bond, we don't get B and Y ion, but we get C and Z ion because the cut is on amine bond. And the special things about this ETD, the PTMs and the side chains left intact. But on the other hand, because you are transferring ion to transferring the electron to your protonated molecules, you need to have higher precursor charges. And it's a bit slower than SCD. So there's a lot of development is ongoing on, and there's dedicated labs is working on the ETD fragmentation. You could also go to last year's summer school talks. Professor Dr. Coşkun Kun in the medicine and his team is working to improve the ETD and more. So now let's talk about how we can set MaxQuant for PTMs. Hamid was showing on Tuesday how to set it. And then here, what we know, we go to the group parameters and we go to the modification tab. And here we have variable modification tab. So the differences between variable modification and fixed modification is that we know on the fixed, our peptide has always the same residue, the same modification on the same residue. But for the variable modification, the same residue might be modified or unmodified. And when you work for phosphorylation, it's also, here we have a serine, threonine, and tyrosine, and you just simply put it on the right side. And it's possible that phosphorylation happens on this serine, or next peptide it was on the tyrosine, or maybe it was happening on two different residues on the same peptide. And the number of modification is shown on the lowest part, maximum number of modification per peptide. And by default, we set it to 5. So we have more than 500 modification on this PTMs and on this modification tab. They are not just the standard modification, there are also some labeling strategies and so, but there is still quite a lot of modification already configured for the MaxQuant. But even if you want to study your own MaxQuant didn't configure, you could go to watch Christoph's video. And then what you need to do, create a new entry on our configuration tab, and you just give the name, and then you will give the specificity, meaning that which amino acid they are targeting, and if there's any neutral losses, and if there's any diagnostic peaks. Because for the serine, we have the neutral losses, but for the tyrosine, we don't have this, and we have the diagnostic peaks. So diagnostic peaks are defined here. And another thing is, if you see on the lower part, it's a modification XMS, and there's also a file on your system. You could also go check how it's been configured if you want. On the MaxQuant, in 2014, from Dr. Sharma et al., they published data sets, and this data set was so deep, and then it showed like 2/3 of the proteome was phosphorylated, and it was a label-free quantification. They did like 40 days of measurement, and they had millions of spectra. And on this paper, MaxQuant computational pipeline for the PTMs was also published. And on the paper, there was four conditions, and one we have unstimulated, and one is mitosis. If you remember in the beginning, you will remember that there's a lot of phosphorylation happens on the cell growth, cell division. So we expect there will be a lot of phosphorylation events happening on the mitosis. And there's also two other condition was there, this EGF. It's good to know, there's a lot of literature to check it. And the other one is about to stopping the phosphorylation event. Let's see what happens. But for us, we came here for the computational reasons. So for us, I think it's more important how the pipeline was working. And so here is the schema of the of this pipeline. So on the A, we see that we have data acquisition, we have our spectra, and then the first step on the B, here we see the phosphosite identification. So here we do some filtering based on PTMs. And on the C, we do some localization, because in the special things on the modification, we know that it happens on the different sites. So we need to give some probability for this localize. And then we also have occupancy calculation. Now let's talk in detail like how the identification happens. So there was slight changes on Andromeda scoring. We discussed this on the earlier day, on the beginning of the summer school, how the Andromeda works. And what's special on the PTMs that we have some modification specific neutral losses. So for the serine and tyrosine, threonine, we have this ammonium loss. And for the diagnostic peaks, we have for tyrosine, we have this ammonium at phosphotyrosine. So what happens in the end? We have Andromeda scoring calculated with these losses and without these losses. So we do a lot of calculation and we optimize this Andromeda scoring, and we get in the end the best score match. This is our theoretical spectrum generation. And so if we have a look at here, the second part, it was saying that Andromeda score filtering and delta score filtering. Let's see where we can find this information. On the global parameter, on the identification tab, we have minimum score for modified peptides. It's set by default to 40. And these numbers comes from this paper. And the paper is about large synthetic peptides. And by default, we don't have any filtering for the unmodified peptide. By modified peptide, we have some preset good score. And then the second thing is, okay, we have Andromeda score, but we also hear the delta score. And what is the delta score? Delta score is the differences between the best Andromeda score for the peptide spectrum match subtracted by the second best Andromeda peptide spectrum matches. So basically the difference is the top two rank of scores. And here it was by default set to 6. Probably you don't play with these numbers, but I think it's still good to know where you can actually go and then see what's happening. So the localization probability. So this is to show us how likely that our phosphosite is really occurring over there, to giving us some statistical power. And then this is calculated as normalized combination of all possible sites for this site was assigned to be modified. So let's look at our example. What we have here, we have the same peptides, but we have 3 different scenarios. Because we know the peptide mass, and we also know the peptide sequences, we could find out there are actually 2 sites are phosphorylated. And then, okay, there are 2 sites can be phosphorylated, but we have 3 different possibilities. Because we say phosphorylation can happen on serine, tyrosine, and threonine. And we make the combination saying, okay, my first possible position is the first element can be phosphorylated, and the 4th element can be phosphorylated. And let's do the Andromeda scoring. On the second combination, we have the first element is first residue is phosphorylated, and the second to last residue phosphorylated. Considering this assumption, we calculate our Andromeda score. And for the 3rd one, we said, okay, the 4th one can be phosphorylated and the last 2. And after calculating the Andromeda score, we took the exponential of these scores, and then we get the probability. After we get the probability, for each site, we normalize this information. So in the, on the first side, we have these 2 tyrosine, and then we know that it could be the phosphorylation, the probability 1 and probability 2. So we sum these 2, and then we normalize it by all of these values. And it's also the same for the middle ones. On the middle ones, we sum this, the first probability score and the 3rd probability score, and then divide by all of it. And the 3rd one is the same. So after calculating the localization probability, there has been some studies. And according to these studies, 0.75 is actually classified as a well-localized site. Okay, so let's talk about occupancy. Occupancy is the fraction of the protein for which of the protein is modified. So let's look at it here. Let's go like this visual conception. So we have condition A, and we have condition B. And what happens, the difference between condition A and B, there's stimulus. So we have increase of the phosphorylation. So it looks like there's 2-fold change, but is it really 2-fold change? Let's have a look in terms of occupancy, because it will give us exactly how this is happening on the condition, on the protein level. To calculate the occupancy, we need to know 3 different numbers. We need to know first phosphorylated peptides, how many number of phosphorylated peptides we have. And we need to know unmodified peptides, and we need to know the protein. How many proteins do we have? Let's look at the condition A. We only have 1 peptide, and on the condition 2, we only have 2. And for the unmodified, on these 3 proteins, we have 2 unmodified counterpart for these peptides, and on the other side, we have only 1. And for the protein, they are the same. But we cannot really compare these ratios within each other, right? It's like comparing our superhero against like a random guy. So it's like comparing against apple or the orange, and then we need to calculate the ratios instead. So the ratios of the phosphorylated peptides, ratios of unmodified peptides, or the proteins. So when we calculate the proteins, when we calculate the ratios, we can have these 3 values, X and Y, Z. And then there was this occupancy formula was established previously. And then here we can just add these numbers. On the proportion, we know what's Y, we know what is Z, and then we can get the proportion. And then we can have an idea about stoichiometry, about the occupancy. This can be informative measurement for the what's happening on the system. And what we know that on the control, we don't expect so much of phosphorylation event. Of course, we cannot really stop this completely, but compared to the extrusion mitosis, where we know that there is a lot of phosphorylation happens, we can have an idea like this occupancy is giving us. So there's a lot of sites has been phosphorylated here. But for EGF, it's very similar to the control group. So for the tyrosine phosphorylation site, we could also have some ideas when we make the box plots. It's very similar to the third condition where we cut and then stop the phosphorylation event with this tyrosine. But it's good to use it to understand the structure, but it's not so used to do further really detailed statistic analysis on this. How we can set MaxQuant for PTM? So we really need to have a full proteome data set for occupancy calculation as well. So here what we see that the upper one has group 0. And then for PTM, it was defined none because this was not enriched. This was just a regular proteomics experiment. And the second one is group 1. And this was enriched for the phosphorylation. And here we also added on the PTM level, which one is phosphorylated, which one is PTMs. And then it's important also these experiment names to calculate occupancy. But sometimes it's not so, if occupancies are not reported, it's because you don't have enough depth on the proteome. So you need to really go deeper to find the unmodified partner of this peptide, and then you can calculate the occupancy. So it's important what is happening here. So there are like 2 modified peptides, 2 modified protein ratios, but it's saying really 2-fold change, or is it like increasing the protein, increasing PTM? So you have to always ask such questions to yourself in the end of the day. So the conclusion wise, many times we always show these PTMs in the aspects of phosphorylation. It's also because the study came with the phosphorylation in mind. There was a lot of improvement on the database size for phosphorylation, but in theory, you could study all kinds of PTMs with MaxQuant. And imagine that if you don't know which modification can be on your sample, then you can simply perform the dependent peptide search. What I like about the MaxQuant is like MaxQuant is really user-friendly, and then you only need to introduce the vendor-specific files, and then it will find out what was the special things about it. So which fragment methods. So we spent a few minutes on the fragmentation methods, but in the end, MaxQuant will find it for you. So there is no need to really think in additional for such things. For Andromeda scoring, this score has been modified and the specific information has been added to improve our identification rates. And localization probability can give us some idea about the sites, how likely really true or not. And then if you want to calculate occupancy, as I told you, as I referred before, you need to have the full proteome too. So in the end, on the phosphorylation is not our only superhero, but on like in the Justice League, we have other PTMs too. So I hope that you will use MaxQuant for your PTM researches. So there will be Perseus tutorial tomorrow morning, and then we will go through the data sets that was used for the MaxQuant or computational pipeline. So we will go through and then see what we can do on the PTMs. Before I finish it, I want to say that I started working at Evotech. So if you are looking for industrial experience, you could also check the Evotech website to like post like some nice jobs you can find. With this, I want to thank you all.
Any questions?
Hi, thank you. My question is about the fragmentation for the phosphorylation. Would you think ETHCD would be more efficient for the fragmentation, also keeping the phosphorylation?
SCD is good, yeah. SCD is good. So, I mean, SCD and ETD, but not CID. Okay. But I think people at the moment, I don't know if using the CID, I think many people are already using the SCD. So If you are using all the HCD, it's fine.
Yeah, because
Mhm.
followed by the ETD, we can set a low energy for the HCD, which
Mhm.
will also, I think would be better for keeping the phosphorylation.
Because they have very labile bond to
Yeah.
attach to them. Yes.
Okay, thank you.